So we're going to get a little more practice with domains because these can get tricky sometimes with our combination and our composition functions. So looking at number 14, and usually with our combinations, the trickiest ones can be these quotient functions. So I'm going to take a look at two quotient functions. So for number 14, we have f of x equals x minus 1, g of x equals x squared plus x minus 2. So for part A, it says find f divided by g, find that quotient function. So let's go ahead and write that out. X minus 1 over x squared plus x minus 2. Easy peasy, right? Except, remember that with our quotient functions, I always want you to check to see if we could factor and cancel any common factors to simplify. So I can factor that denominator, right? My denominator, x squared plus x minus 2. This gives me, if I factor x plus 2 times x minus 1. And then I still have that x minus 1 up top. So I'm able to cancel out that common x minus 1 factor. So this simplifies to 1 over x plus 2. So if I said, what's the quotient function? You would say it's equal to 1 over x plus 2. That would be your final answer because you want to fully simplify and cancel. However, when it comes to the domain, anything that's excluded from either of the original functions or from that combination function also has to be excluded from the domain of the quotient function. And remember, if we have a quotient function, there's that extra exclusion that the function in the denominator can't equal 0. So if we look at the combination function, so if we're trying to find the domain, right? So for the domain, just looking at that f over g function, I know that the denominator can't equal 0. So that would mean that x can't equal negative 2, right? Looking at that. But I want to go farther than that, and my original denominator, oops, this must be a highlighter. My original denominator, x squared plus x minus 2, cannot equal 0 either. My original denominator had two factors in it, x plus 2 and also x minus 1. So that means that I also have to exclude an x value of 1 because that would also create a 0 in that original denominator before I simplified it. Okay, so f of x itself is a polynomial function, no domain restrictions. G of x, no domain restrictions. But when I get to the quotient, I'm looking at the original denominator function before I factored and simplified to calculate the domain. So my domain needs to exclude not only negative 2, but also positive 1. So the domain of f divided by g, I'm going to go from negative infinity to negative 2, negative 2 to positive 1, and then positive 1 to positive infinity. And that's my domain. Okay, so flipping the order of this, now for part C, we have g up top, x squared plus x minus 2, and then x minus 1 in the denominator. And we know from before that I can factor that numerator now into x plus 2 times x minus 1. And now canceling, x minus 1 over x minus 1 cancels. So this gives me x plus 2. Okay, so that's my quotient function. However, for the domain, I can see that my overall function after I simplified doesn't have any restrictions. It's just x plus 2. We can put anything in for x, any real number, and we won't have any issues. But if we look at the original denominator function, originally we had x minus 1 in the denominator. So that means I need to exclude 1 from my domain. So negative infinity up to 1, 1 to infinity is my domain. Okay, so when you're calculating the domain, A good technique is to look at it before, look at your function before you started simplifying and canceling. And in particular, this will come up quite often with your quotient function, so remember that restriction that the denominator function can't equal 0. Okay, so for composite functions, for number 15 it says find the composite function f of g, and we also want to find the domain after that. So first let's go ahead and find the composite function f of g. So this will be f of g of x, which is f of 1 over x, which equals 1 over x plus 2. Okay, so that's all fine so far, except I just created what's called a complex fraction. I've got a little fraction in the denominator of a bigger overall fraction. So I need to get rid of that 1 over x in the denominator. And there are different techniques to kind of simplify this to get this not in complex fraction terms. But one is, if you look at any kind of mini fractions that are appearing in your bigger overall fraction, look at all of the denominators. In this case, we've only got one fraction that makes an appearance. But if you have multiple fractions, find the LCD, the least common denominator, across all of their denominators. In this case, the LCD is x, right? I only have the one fraction with one denominator. So if I multiply every term on the top of my overall fraction and every term on the bottom of my overall fraction by the LCD, by x, that will clear out fractions and keep that ratio balanced from numerator to denominator. So as long as I multiply the top term by x, multiply the bottom left term by x, multiply the bottom right term by x, that ratio remains balanced. And then what happens is down here, where I have x, and you could call it x over 1 if you want, the x in the numerator over the x in the denominator cancel out. So up in my overall numerator of my bigger fraction, I have 1 times x, which is x. In the bottom left, now I just have 1 over 1 since the x is canceled, so that's just a whole number 1. And then I have plus 2 times x, so 1 plus 2x. So my f of g function equals x over 1 plus 2x. Fantastic. Now when it comes to my domain, I do want to exclude any values, just looking at the composite function, right? So let's look at the actual composite function. So for this f of g function that I just came up with, if I look at my denominator says 1 plus 2x, and I know that that denominator can't equal 0, right? 1 plus 2x. So wherever it does equal 0, I want to exclude those x values. So I could subtract 1 from both sides to get 2x equals negative 1, divide all the way across by 2. So when x equals negative 1/2, that denominator of that composite function equals 0. I don't want my denominator to equal 0, so that means that's one excluded value in my overall domain of my composite function. X can't equal negative 1/2, that's an excluded value for my domain. But remember how I told you it was a good technique to take a look at your original denominator as well before you started simplifying stuff. So before we started messing with stuff, I had this fraction 1 over x, and that also can't equal 0, right? So I need to pay attention to my inner function, right? Are there any excluded values from g of x, from my inner function? And for g of x equals 1 over x, its denominator can't equal 0. So that means I have a second excluded value that x can't equal 0. Because if x equals 0, then when I'm evaluating f of g of x at 0, if I try to evaluate f of g of 0, g of 0 doesn't exist, right? 0 isn't in g's domain, so right there we have a problem. So I'm going to exclude not only negative 1/2, but also 0. So the domain for my composite function is going to be from negative infinity up to, I'm going to list negative 1/2 first, because it's the farthest to the left on the number line between negative 1/2 and 0. So negative infinity to negative 1/2, union symbol, negative 1/2 up to 0, union symbol, and then 0 to positive infinity. And remember, use rounded parentheses everywhere because we can't equal negative 1/2 and can't equal 0 for our domain.